Hello, in this lesson about curve sketching, we're going to do two more examples that I will try to keep the length of the recording in control. And in these two examples, one has exponential function and the other one has logarithm function. So let's start with the first one, and we're going to go through each one of these items to to go through these steps. All right. First of all, the domain, of course, is all real numbers. All real numbers. And secondly, intercepts. Intercepts. The easiest intercept is to find the y-intercept, right? To find y-intercept, we just set x equals 0. When x equals 0, and this will be 0, 0, so that equals to 0. So in fact, you can see x-intercept and y-intercept are the same. Okay, so this is the y-intercept. Okay, y-intercept. If we have a y-intercept, we'll have just one. Okay, and let's look at x-intercept. Okay, x-intercept actually is pretty obvious, but we're gonna go through the steps. We're gonna go through the steps. Sometimes we have more than one x-intercept, by the way. Okay. To get x-intercept, we're going to set y equals 0. We're going to set the whole function equals to 0. Okay. Which is that equals to 0, right? We set y equals 0. Okay, f of x equals to y. So this will lead to x times e to the power x equals to 0. We know that e to the power x is always positive, right? So for this product, for this function to be equal to 0, and we get x equals 0. Okay, because e to the power x is always positive. It's always a positive for any real number x. Okay, so this is domain and range for e to the power x for any real number x. All right, we've done the easy part. Let's look at symmetry. Let's look at symmetry. Symmetry typically can be found by checking whether function is even function or odd function, right? So f of negative x. Okay, so we're going to start with f of negative x. Okay, we have f of x and we have f of negative x. X replaced by negative x. Okay, and apparently f of x is not going to equal to f of negative x. All right, so it's not even since f of x is not equals to. This is just definition. Okay, this is definition of even function. Okay, so when input are opposite, the output are not the same, but they're also not opposite to each other. Okay, and it's not odd because for odd function, right, for even function, for opposite input, we get the same output. Not even, then this is not true, right? For odd function means that f of negative x should equal to negative of f of x. And this is obviously not going to be true because if we put negative sign in front of f of x, we're going to get a negative of x times e to the power x. So they're not the same. So this is still not true. So we have neither even nor odd. Okay. So there's no symmetry. There's no symmetry. Asymptotes. Vertical asymptote, we certainly don't have it because its domain is all real numbers. Okay. Horizontal asymptote. Horizontal asymptote, right? So let's write down no vertical asymptote. Okay. They are horizontal asymptote. Okay. Well, x is approaching, so horizontal asymptote is found by taking derivative, taking limit when x is approaching infinity or approaching positive infinity or negative infinity. So when x is approaching positive infinity, x is approaching positive infinity, this is approaching infinity. So this whole thing approaches positive infinity. Okay, so doesn't approach a constant number. So it doesn't have horizontal asymptote in that direction. How about when x is approaching negative infinity? Okay, so I should put the limit over here. Okay, sorry. Okay, so that limit should be there. All right, but when it approaches negative infinity, what do we get? When f of x, when x is approaching negative infinity, right? So we get x times e to the power x. This piece is going to be approaching 0. X is approaching negative infinity. So and if we do something, we could make it into a, because we have an indeterminate form, right? When x approaching negative infinity, x approaching negative infinity, e to the power negative x, I'm sorry, e to the power x approaches 0. So we could write down, in this form, okay, this way, okay, x e to the power of negative x. Okay, the reason we're gonna write it down this way so we can use L'Hopital rule. Okay, so we basically flipped over e to the power x and put it in the denominator. So when x approaching negative infinity, negative x is going to approach the positive infinity. So e to the power negative x is going to be approaching positive infinity. So we have an infinity over infinity situation. So L'Hopital rule would apply. As L'Hopital rule applies, we're going to take a derivative on both top and bottom. Okay, and the derivative of the top is 1. The derivative of the denominator, we're going to use a chain rule. Okay, we're going to use a chain rule. When we use a chain rule, what do we get? We are getting negative e to the power of negative x. Okay, and that when x approaching negative infinity, the numerator is finite. Denominator approaches infinity, so the limit is going to be 0. So we have a horizontal asymptote, which is x-axis, right? Because this is a y equals 0. So we got a horizontal asymptote, which is going to be y equals 0. Y equals 0 is really x-axis. Okay, we got the asymptotes. Let's look at the intervals. Let's look at the intervals of increasing and decreasing. So that will require us to find the derivative. Okay, so interval of increasing, decreasing. And let's look at this. Okay, we got the function. Okay, so let me bring the function with us. I'm going to take a derivative, right, to find critical numbers, local max, local min. And the derivative of this function would be, we're going to apply product rule. Okay, so f prime. And this is going to be derivative of x, derivative of e to the power x. Okay, prime. And that will be equals to, the derivative of x equals to 1. So we just got e to the power x. And times x multiply e to the power x. Factor, because looking ahead, we're going to find the critical numbers, right? To find critical numbers, we have, if we get a factored form, that would be very helpful, okay? And that's 1 plus x. And then we can set the derivative equal to 0. Okay, we're going to set the derivative equal to 0. Setting derivative equal to 0, the purpose is to find critical numbers. So we're going to set the derivative equal to 0. Well, you can see the derivative domain is also all real numbers, right? The domain of derivative is also all real numbers, which is the same as the domain of the function, right? So this tells us there's not the category of critical numbers where the derivative is undefined. Okay, so we don't have that category of number. So we just set it equal to 0. E to the power x is always a positive. So 1 plus x has to be 0. As a result, x equals to -1. So we got only one critical number. So let's look at the the sign changes of first order derivative. And that's pretty obvious because e to the power x is always a positive, right? So we're going to just look at the number line. Okay, so we're going to look at the sign of the first order derivative, right? First order derivative function. And it is equal to e to the power x multiply 1 over x, right? This, first of all, you can see the sign of 1 plus x, right? The sign of 1 plus x. It changes sign at -1. So we got a number line at the point of -1, right? And then continue on the number line. We don't have other critical numbers. So when x is less than -1, right? When x is less than -1, then this is going to be negative. Okay, these are going to be negative. At -1 is 0. After -1, when x is larger than -1, it's going to be positive, right? You can see the derivative changes sign. Oops, sorry. All right, the derivative changes sign at -1. So to the left of -1 is negative, to the right of -1 is a positive. And when we for 1 plus x, but e to the power x is a positive. So that doesn't change it doesn't change the sign. So it stays the same. All right. So with that observation, we can apply first order derivative. Okay, we can apply first order derivative. Oh, by the way, I'm sorry, the max min, we're gonna do it on the next step. So we just tell the interval of increasing and decreasing. Okay, so on this interval, so the derivative tells the increasing, decreasing of the function. Okay, so f of x increases in the interval from negative infinity to -1. And f of x increases, okay, increases, decreases, okay, in the interval of -1 to positive infinity. Actually, local minimum is already determined at a -1, okay? But obviously, since we only have one critical number, right? We only have one critical number. And we're not going to have local maximum. We're not going to have local maximum because that's only one. That's only one. All right. So we got a local minimum. We got a local minimum. So the next, to answer the question next, okay, we got a local minimum by first derivative test. Okay, you can say by first derivative test, okay, local minimum at -1. And the value, right? So this is where, and the what is going to be f of -1. And that's going to be -1 e raised to the power of -1. So the local minimum is a negative over e. All right, so that's the local minimum. So if you want to express local minimum where and what, right, it's going to be -1 of, and then comma f of -1. That's equal to -1, -1 over e, -1 over e. Okay, so that's the local minimum. We don't have local maximum because when x approaches infinity, positive infinity that approaches positive infinity, right? We did that on the horizontal asymptote. All right, so let's check out the last two questions, okay, about concavity. On concavity, we're going to have to find second order derivative, okay? Second order derivative is a derivative of first order derivative. So we're going to take a derivative. I think we're going to use this form instead, okay? Of course, you can use either one, okay? You can use either one. So we can use either this one or the next one, whichever one you feel comfortable, because they're the same thing. It's just you have to use the product rule anyway, right? So this is the first order derivative. Okay, really, it's a pretty personal choice. So let's do second order derivative. Okay, second order derivative f prime, double prime, okay, equals to, if I'm using this latter one, I'm going to use product rule. So derivative e to the power x is e to the power x. So the first part is done by differentiating e to the power x. And the derivative e to the power x is the same. The second part is going to be taking derivative of 1 plus x. Okay, the derivative of 1 plus x is 1. Okay, and e to the power x times 1 stay the same. So, and then we're going to factor down the e to the power x, right? We're going to factor out the e to the power x, e to the power x, e to the power x factored out. So we're going to get 2 plus x, 2 plus x. And the change of concavity, right? Change of concavity. So if there's a change of concavity at that point of change and there's the inflection point. So obviously we can see the sign change, right? So the sign change, the sign of 2 plus x. The sign of 2 plus x is the same as the sign of e to the power x times 2 times x, times 2 plus x. Because e to the power x is positive, okay? So that marks the derivative of second order derivative, right? So we're going to have, so this picture is going to be similar. Okay, so -2, all right? But this is about f double prime. This is about f double prime. So we want to mark that properly so we know what we are doing, okay? F double prime, when x is less than -2, is going to be the 2 minus x is going to be negative. Okay, this is actually very similar to, you know, when we work with the first order derivative. At -2, and it's 0, right? The second order derivative equals 0. After -2, it's going to be positive. So when x is greater than -2, when x is greater than -2, we got a positive. Okay, less than -2 and larger than -2. Okay, all right. So this tells us that in the interval from -infinity to -2 is concave down. On the next interval from -2 to infinity, that's concave up. So at -2, there's a change of concavity. Okay, change of concavity at -2. Okay, therefore, the inflection point is, okay, x equals to -2, but when x equals -2, what does f of x equal to? So f of -2, this is the point, right? So we need to, when talking about inflection point, we need to give a pair of numbers. Not only we need to give the x, right, which is -2, we also need to give the value of f of -2, which is the y value. So let's evaluate the y value. Our function was x times e to the power of x. Sorry, e to the power of x. Okay, so when x equals to -2, and this will be, x will be substituted by -2. This will be -2 over e squared. E to the power -2 is e squared under 2. All right. So we got our inflection point. Our inflection point is Now we can put it in place. -2, okay, -2 and -2 over e to the power of squared. Okay, we'll keep this number. You don't need to approximate it because that's going to cause the loss of precision. Okay, so let's put this together. We're gonna do the sketch. We're gonna do the sketch. We're gonna sketch the curve. Okay, I know that we can get the picture at our fingertips, but we're gonna gradually put things in place. Okay, gradually put things in place, and as we go over these characteristic, we get from the function, right? We're not gonna just plot the points. We have a point. We have an inflection point, and we have a local minimum. This is a local minimum, so I'm going to mark this point. We're going to mark this point first, right? So this will be the local minimum. So red dot, a point, local minimum. Okay, local minimum. I'm going to make some adjustments to the view. Okay, so we may need more adjustment later, but for now, this is the picture we got. We get one dot. This is a local minimum. Point of inflection point. Okay, inflection point. We're gonna use a blue dot. How about that? Okay, inflection point. So there's a change of concavity. What else we have? We have intercepts, right? X-intercept, Y-intercept are the same. So intercept, I'm going to put a 0 as a dot. Okay, so we can see the curve is going to come to negative infinity, right? It's going to be approaching zero from above or below, right? When we were looking for horizontal asymptote, you see it actually approaching zero from smaller than 0. Okay, you can see the curve actually is like underneath, going down here, and then goes up. Okay, so that's our anticipation. That's our anticipation if we don't have a calculator, right? Because in this way, okay, I'm just going to sketch it, right? So this is going to approach infinity. That's x approaching negative infinity, the curve approaches 0. And in this direction, it's going to keeps going up. Something like that. It doesn't touch the x-axis except at a 0, 0, 0. And this point is a point of inflection. This is point so there's a concavity change. So this is a concave up, and this piece is a concave down. Okay. But with this kind of assessment, and now, we're going to just plot the function in place. Okay, so I'm going to graph the function. And most of the software will do a good job for you just to confirm. Sometimes it's fun to guess before we push the button. So that's the picture. That's the picture, right? We can make a little more adjustment on the view, right? So we can put it on 3. On the other side, we can put it -4. And on this piece, we can get a 3. You see how the picture looks like. Something like that, yeah. So this is the third example in this section. We had two more recordings on this. And this recording, as I planned, we're going to do an exponential, and then we're going to do a logarithm. So let's look at the logarithm. Okay, let's look at the logarithm involved curve setting domain. Okay, when logarithm involved domain, we need to be careful about domain. So in this case, x is greater than 0, x is larger than 0. So then the derivative will be larger than 0 because you're not going to have derivative. Function is not even defined there. So the graph is only going to be to the right of y-axis. Okay, so keep this in mind. It's very important that we have this domain observation. Then you say, how about 1 over x? 1 over x is automatically covered because x cannot be 0 in this case. X is larger than 0. It's just one part of the graph, of 1 over x. All right, so these two are just combined. Okay. X-intercept. Do we have x-intercept? Do we have y-intercept? Okay, we start with the easy one first. Y-intercept. Well, to get a y-intercept, we need to set x equals 0. But at x equals 0, it's undefined. We have none. We don't have a y-intercept. Do we have an intercept? Right, so let's look at, do we have an x-intercept? X-intercept. To get an x-intercept, we're going to set the whole function equals 0. Right, we set a y equals 0. If we set a y equals 0, and all of these solving activity is going to be in the domain. So when we solve for it, what do we get? We set it equals to 0. This is to set y equals to 0, right? And then we got 1 over x equals to negative ln x. Negative ln x is ln x raised to the power of -1. And that is also ln of 1 over x. So we have a situation, we have 1 over x, okay, equals to ln of 1 over x. And this solution that x has to be positive doesn't have a solution, right? Doesn't have a solution. If there is a solution, what would it be? What would it be? So we'll be asking this question, right? What number will cause ln, right? So you think of ln, think of 1 over x as omega, which is ln omega. Does such number exist? Does such number exist? Provided that omega is positive. Okay, the input is the same as output. The input is the same as output. Does that ever happen for ln x? Okay, omega need to be positive. Is there a solution? I hope you guys understand. Is there a solution to this question? Is there a solution? Okay, what does this imply? Input is the same as output. Okay, such solution does not exist. Such solution does not exist. All right. You can pause and try it on your own to see if there's a solution. Okay. There are multiple, studies you can look at on this. Okay. The definition from here, if this were true, and that means e to the power omega is going to have to equals to omega. Or equals to omega. Okay, this is not true. This cannot be true because you can try as many numbers as you want. This is never going to be true. Okay, this is never going to be true. Okay, so no solution. So there's no solution. No solution means what? So no solution, meaning there's no x-intercept. There's no x-intercept. Okay, there's no x-intercept. All right, if you have any doubt, just take a pause and work on these logarithm thing, okay? All right, no x-intercept nor y-intercept, okay? So let's look at C. Okay, so let's see what the question for C. Symmetry. We definitively do not have symmetry with respect to y-axis because the domain is just x greater than 0. We cannot even assume the negative input, right? Because they're not in the domain. So no symmetry, right? Not even, right? No symmetry with respect to y-axis. It is not even, okay? Not an even function. Is it odd? No, not possible because we cannot have a negative input. We cannot have input. No symmetry with respect to origin, okay? No symmetry with respect to origin. Okay, that's the odd function. So it's not an odd function either. Okay, not an odd function. Not an odd function either. Okay. Asymptotes. Okay, so let's look at what x is approaching positive infinity. We're not going to take a limit for x approaching negative infinity because as x approaching negative infinity, the function is not defined there, right? So the only oh, we obviously are looking at horizontal asymptote, right? Horizontal asymptote. For our horizontal asymptote, we're only going to observe the limit. Okay, normally we observe the vertical asymptote first. But since we started with horizontal, we just do horizontal anyway. Okay, so we're going to observe this limit when x approaching positive infinity. When x is approaching positive infinity, this piece is approaching 0, right? And this piece is approaching positive infinity. 0 plus infinity. 0 plus infinity. So this is going to be approaching positive infinity. It's going to be approaching positive infinity. Okay. And if you have any doubt, right, because this is not in product form, but there's no subtraction either. So when x approaching zero, I'm sorry, when x approaching infinity, 1 over x approaches 0, and this approaching infinity. So there's no doubt about that. So it does not approach a constant, okay? So let's look at the vertical asymptote, okay? Vertical asymptote. The vertical asymptote, I think it would be x equals 0. X equals 0, okay? Because x can approach 0 as much as possible, okay? So when we look at the limit, right, because we have to do the limit inside the domain, right? We have to do the limit inside the domain. So we're going to look at this limit as x approaching 0 from larger than 0. Now, what are we getting here? Okay. Well, x is approaching 0 from larger than 0. Okay, we're applying the definition of vertical asymptote. You may like to pull out those index cards, right? X cannot be 0. So we're just considering x approaching 0. X cannot be 0, but x approaching 0 from larger than 0. Okay, so we're going to observe that limit. Well, x approaching 0 from larger than 0, this piece is approaching positive infinity. This piece is approaching negative infinity. So have infinity subtract infinity. Infinity subtract infinity, we don't know what is going to be equal to, right? So in this situation, we will have to do something. Okay, so we're going to find the common denominator. Okay, the common denominator is x, and the top is 1 plus x times ln x. All right, so as x approaching 0, from larger than 0, the bottom approaching 0, the top, right? When x is approaching 0 from larger larger than 0, this piece approaching negative infinity, and it looks like we cannot use L'Hopital rule. We cannot use L'Hopital rule. So how do we estimate this limit? How do we estimate this limit? It doesn't exist, okay? It does not exist for sure. This way it doesn't work. It doesn't work, okay? But no fear, okay? We're gonna change the way. We're gonna look at, because if we can produce a way, because we know this limit is not gonna, it doesn't exist. So we're gonna convert it to a product form, okay? So this is what we're gonna do. We're gonna factor out the 1 over x. Okay, so between these two, we're gonna factor out the 1 over x. When we factored out 1 over x, this piece doesn't have it. We have a x times ln x. X times ln x. Let's see what we got, okay? 1 over x times 1, we get back there. 1 over x times ln x, what do we get? Well, x is approaching 0 from larger than 0. This piece approaching positive infinity. What is the piece approach in the parentheses? Right? As x is approaching 0 from larger than 0, this is approaching 0, and this is approaching negative infinity. Listen up. So something approaching 0 and multiply ln x, which approaches negative infinity. So for this, we're going to do a separate assessment. We're going to do a separate assessment, okay? We cannot apply limit law here. We cannot apply limit law here, okay? So I just want to see what will be the limit of this piece. I think we did something similar in L'Hopital rule, okay? So this will give us, it's an indeterminate form. It's an indeterminate form. So this piece, okay, as x approaching 0 from larger than 0, this piece approaching negative infinity and x approaching 0. So we're going to create a situation that we can apply L'Hopital rule. We can apply L'Hopital rule. So when x approaching 0, this approaching negative infinity, this approaching positive infinity, so we can apply L'Hopital rule. So let's apply L'Hopital rule that the top has, going to be the derivative, right? The derivative of the top is 1 over x. The derivative of the bottom is negative 1 over x squared. All right? Okay? Now, simplify, we will get negative x. So this limit equals 0. This limit equals 0. So go back to see this piece, the limit for this piece as x approaching 0 from larger than 0. This piece is approaching 0. Approaching 0 plus 1 is going to be approaching 1. Okay, so this parentheses approaching 1. 1 over x approaches the infinity. So now we are certain this approaches positive infinity. So this established, okay? Okay. This establishes that the vertical asymptote is x equals 0, which is the y-axis, i.e. the y-axis. Okay, so if you go back to see the definition of vertical asymptote, you're going to find there's one of the definitions there. Okay, all right. So the asymptote issues are resolved. Vertical asymptote, horizontal asymptote are resolved. We don't have any horizontal asymptote. So let's look at the interval of increases and interval of decreases. And we're going to take a derivative. We're going to take a derivative to find critical numbers of those sort. And also be mindful because the domain of the function is x greater than 0. So, okay. So let's take a derivative. So derivative would be negative 1 over x squared plus 1 over x. 1 over x. So we make a common denominator. Okay, so this one already have the common denominator x squared plus, and 1 over x is x over x squared. So now we got the common denominator, and one more step, we're going to keep the common denominator. The top will be just x minus 1. And we set first order derivative equals 0. We set derivative equal to 0, right? To find critical numbers. And now let's look at the domain of derivative, first order derivative. What's the domain? The domain is still x greater than 0, guys. Okay? The derivative is not x not equal to 0 because only within the domain of the function can we find the derivative. So domain is still x greater than 0. So we don't have extra number. We don't have extra number for critical numbers where the derivative does not exist. Okay, so you can see where the derivative does not exist. From this form is 0, right? Well, 0 is not in the domain at first place, all right? So we set the derivative equals 0, and we have the fraction form for the derivative denominator cannot be 0. It's ensured not equal to 0. So the only way for that, for the first order derivative to be equal to 0 is x minus 1 has to be 0. So we get our one and only critical number. Our one and only critical number. You can call it C, you can call it 1. Okay, so I'm going to name it 1 because it's so special. It's so special. And we're going to give the interval of increasing, decreasing. Okay, the denominator positive. Numerator changes sign, right? So obviously, if you have a number line here, this will be pretty straightforward. Okay, at 1. So to the left of 1, right? By the way, we are working with the first order derivative. So this is about the first order derivative sign, right? So to the left of 1 is negative. At 1 is 0, right? Larger than 1, positive. So the interval, so you can say f of x decreases in the interval from not a negative infinity, from 0 to 1, okay? Increases, f of x increases, be aware of the domain of the function, increases in the interval of 1 to positive infinity. And here we go, we already have a local minimum. We already have a local minimum. Okay, so we don't have a local maximum. So we have a local minimum by first derivative test. Okay, by first derivative test. Okay, we got a local minimum because the first order derivative changes from negative to positive. Decrease, increase. So local minimum at 1. At 1. Okay. And what is the value? So at 1, the function's value, we're going to plug in the function. So what is the function? The function is 1 over x plus ln x. So my input is 1, so this is 1. ln 1 equals 0, so this is 0, so the local minimum is 1. F of 1 equals to 1. We'll call it local minimum. Concavity. Concavity, all right? What do we have here? What do we have here is that we need to find second order derivative, right? Second order derivative is a derivative of first order derivative. So we got our function, we got our second order derivative. I'm going to copy the whole thing here to decide which one we're going to use for second order derivative, right? Which one is easier? If we use this form, we're going to be using quotient rule. If we use these two, it's this power rule, right? So let's find second order derivative on the first order derivative. So the derivative of the first order derivative, is going to be second order derivative. So let's use power rule, right? Power rule, you can write it as negative x to the power of negative 2 plus x raised to the power -1. If you like to go that way, okay? So we're going to differentiate the whole of these. And we're going to differentiate the whole of that. All right? And let's see what we got. Power rule. Okay, so we got -1, multiply -2, and x raised to the power of -3. And on this part, actually, because I'm going to write it as a fraction form, so it's going to be 1 over x squared. This is going to be a negative. Okay, this is going to be a negative. All right, so this is going to be +2. And you can pause here if you're not following me. Okay, so we're going to write it as we're going to write it as in this form. Okay, x raised to the power +3. Okay. And common denominator is x raised to the power 3. So now we're going to keep x raised to the power +3. And we're going to have this piece will be x over x raised to the power 3. Does that make sense? Okay, so there's going to be 2 minus x. 2 minus x. All right, so we got second order derivative. And this is to determine concavity. This is to determine concavity. Remember, the domain of second order derivative is still greater than 0. Okay? The domain for second order derivative is still going to be greater than 0. So now let's look at the sign. Okay, so let's look at the sign of second order derivative. Okay, the denominator in the domain is going to be positive regardless. So 2 minus x decide the sign. Okay, so look at the number line. The point of change, the sign change is a +2. +2, right? When x is smaller than 2, larger than 0, right? So here there's a 0, okay? This side doesn't go to -infinity. It's, it's getting closer and closer to 0, but never touches 0. Okay, that's what domain larger than 0 means. For the second order derivative, you look at 2 minus x, right? When x is less than 2, it's going to be positive. At 2 is going to be 0. At 2 is going to be 0. There we go. If x is larger than 2, this is going to be negative. Sorry. Negative. Well, you don't have to do this number line thing if you get it. Okay, I just want to be a little bit more visual. So second order derivative, you can see changes the concavity at 2 from concave up to concave down. So 2 is there's an inflection point. Okay, so there's an inflection point. So this is a concave up. Okay, on this other side is a concave down. Okay. So we got that. So we have an inflection point. That inflection point is 2, comma, f of 2. So we're gonna find the value for f of 2. What is f of 2? We're gonna plug in this f of 2, right? Go back to the function. The function is 1 over x plus ln x. When x equals 2, this is going to be 2, and this is going to be 2. So our inflection point is 2 comma half plus ln 2. So this is just a number. This is just a number. So now we are ready to, so let me mark this, inflection point. There's a change of concavity, okay? The definition of inflection point is that there's a concavity change. All right, so let's sketch it. Let's sketch it. Okay, so we got started the graph, the rectangular coordinates. All right. We have no intercept here. We have no x-intercepts nor y-intercept. And we don't have any picture on the left on x equals negative, right? So what we can do, we can adjust the picture just from 0 to just on this side, okay? Just on that side. So if you like, we can have, we're gonna adjust it a little bit later. So let's look at what do we have. We have a local maximum. Oh wait, we have a local minimum, sorry. Yes, we have a local minimum. The local minimum is f is 1 comma 1, right? F of 1 equals 1. So local minimum is 1 comma 1, right? So I'm gonna plot this point in the picture. Local minimum. I'm gonna make it a red dot right there. Okay, point of inflection, right there. Point of inflection. Point of inflection, we're gonna use blue dots. Where did it go? To something, right? Half is somewhere there. We're going to have to make some adjustment. So 5, this should have it, okay? So change of concavity, when x is approaching 0, remember that vertical asymptote we try to find, right? Vertical asymptote, where did we do the vertical asymptote? When x is approaching 0, from larger than 0, the function approaches positive infinity. So this tells us the curve is going down like this, decreases, right? And increases, goes up. Okay, that's the, the horizontal asymptote tells us as x approaching infinity, the function goes to positive infinity. So if you are to sketch it, if we are to sketch it, right? So we're gonna combine these information, right? Because in this direction, it's going to be coming down and change of concavity. This is concave up and concave down, something like that. So that's a sketch. We can sketch it. We can sketch it. Of course, we would get a perfect picture if we just use the software to plot it. Okay, so I'm going to just do that, finish it with the last step, which is just sketch it. So we have a better sketch with the machine. Boom. It's about right. Okay, so we're about right. So that's the sketch of the curve. Point of inflection, and that's local minimum. Concave up to the left of the blue dots, concave down. So if you want to see a little bit more concave down, we can make that interval just a little bit like this. Okay, so let's see if we can, yeah, you can see concave up, right? This piece of concave up, and the next piece concave down is kind of tutoring all of it. It still goes up, but it's there's a little concavity that facing down. All right. I think I want to conclude this lesson. It's just with two examples, one for exponential, the other one is for logarithm. It involved the curve sketching. Thank you for watching.